Matter and measurement. Science begins with observation, and usually that requires accurate and precise measurement. The metric system, developed by scientists, has been developed to provide natural units based on physical constants and using powers of 10. In the metric system, we have base units for length, the meter, for mass, the gram or kilogram, time in seconds, and temperature in Kelvin. To measure smaller or larger amounts, we add prefixes to the base units. Here we see a series of powers of 10, 1,000, 110, decreasing each by a step of 10. Or we could go up the opposite direction. To convert to a smaller unit, we move the decimal point to the right or multiply. We get units like deci, centi, milli. To convert to a larger unit, move the decimal point to the left or divide. We get units like deca, hecto, kilo. Now the units to the right of the base unit are smaller than the base unit. So each move right is 10 times smaller, or 1/10 of the unit to the left. Whereas units to the left of the base unit are larger than base unit. Each move left is 10 times bigger than the unit to the right. Left to right, right to left, moving the decimal point. Now, some students, in trying to visualize this, left to right or decimal points aren't as helpful, so maybe looking at a metric ladder can be a good way to proceed. The decimal can be said to move the same amount of times as the number of steps it takes to get from the first unit to the last unit. So if you go up one step, that's like 1 power of 10, 10. But if you go up 2 steps, that's like 10 times 10, 100 steps, and so on and so forth. Up the ladder, you move the decimal to the left. This means you are dividing. Down the ladder, you move the decimal to the right. This means you are multiplying. Now, before we go on, notice that we have numbers at the top of this slide. The numbers at the very top are regular numbers, 10,000, 1,000, 10, 1. On the bottom, though, we have the same powers of 10 expressed in scientific notation. We're going to be learning how to use a button on our calculator that allows us to enter things in the calculator the same way that we might write them on a piece of paper. And we'll learn more about scientific notation later in this presentation. For now, let's look at the base units of the metric system. Some letters are uppercase, some are lowercase, some are straight, and some are slanted. For example, the symbol for length is a lowercase l, but it is in italics, slanted. The unit is the meter. We abbreviate that with a straight lowercase m. That's because we use lowercase m that's slanted as the symbol for mass. The unit's gram. The abbreviation is g. If we're talking about liquid volume, that's also a base unit, and the unit is the liter. Notice our abbreviation is an uppercase L to avoid confusing it with the symbol for length. Time and temperature both begin with T. So time is lowercase t, and delta T with a lowercase means a change in time. The unit is the second. Whereas capital T is used to refer to temperature. And delta T here means a change in the temperature of the energy of the system. And we can measure the average kinetic energy with the unit of temperature, the Kelvin scale. Now, the last item shown here is something we won't use a lot in biology, but it's extremely important in almost every other science class that comes afterwards, and this is a way of keeping track of the amount of substance. We'll use the lowercase n to measure the amount of substance, the number of particles. The unit is a mole, which has a certain numerical expression that's very large that requires scientific notation. You won't need that really for biology, but it does prepare you for what science courses you might take in the future. The base units, now let's make sure we understand how we use them with different instruments, different tools for measurement. For example, if we're going to measure distance, length, we use a ruler or a meter stick, and we might have different size units of length from smallest to largest, the millimeter, the centimeter, the meter, or the kilometer. 1,000 millimeters equals 1 meter, 100 centimeters also equals 1 meter, and if we have 1,000 meters, that equals 1 kilometer. Suppose instead of measuring distances or lengths, we want to measure the volume. Well, we could use a ruler as well if we're measuring the dimensions of a solid, but more likely we're going to be measuring a liquid, and we're going to be using a graduated cylinder. A graduated cylinder is a tube that has little markings on it, grades, that are similar to the lines that we might see on a metric ruler. Here, from smallest to largest, we have milliliters, which is little m, capital L liter, the base unit. And if we need anything more, we can talk about deciliters or kiloliters, that sort of thing. Now, an interesting wrinkle comes if we compare the kind of measurements that we can make of a solid with a ruler with the things that we measure of a liquid with the graduated cylinder. Here we have a cube, and you'll notice this cube is made of a whole bunch of tinier cubes. In fact, in this particular cube, each side is 10 tiny cubes long, so 10 times 10 times 10 gives us 1,000. And so that's 1,000 cubic centimeters, 1,000 cubes, and those 1,000 cubic centimeters equal 1,000 milliliters in the metric system, and 1,000 milliliters equals 1 liter, and that's very nice and tidy. So you can easily and quickly convert from a solid measurement of volume to a liquid measurement of volume, and vice versa. So this is a unique, powerful, useful aspect of the metric system. We're going to measure mass. We use a scale, a balance, electronic balance, with the units ranging from smallest to largest, from, let's say, milligrams to kilograms. And of course, if we wanted to measure temperature, we'd use a thermometer. If we wanted to use time, we'd use a clock. That's fairly straightforward. Now, an important detail about the meter stick needs to be understood in order to use it effectively. It is divided into 100 equal numbered parts. Each of these numbered divisions is 1 centimeter long. Thus, 1 centimeter is 1/100th of a meter, or 0.01 meters. Now, you got to remember that the centimeters are further divided into millimeters, and you don't see numbers for the millimeters. You see numbers for the centimeters, and then you have 10 little lines between each number. Those are the millimeters. And this is important because oftentimes meter sticks or metric rulers have two sides, and the other side will have English units like inches, feet, or yards. And we don't want those. If you use the wrong side of the meter stick, the numbers that you give me could be off by a factor of 25 or 30, something like that. You know, it's not just wrong, it's wrong times 25. So we want to avoid that. And just remember that in a metric ruler or meter stick, the numbers are typically centimeters, while the very many tiny lines are millimeters. Now, the number of lines does limit the accuracy of our measurements. Here we have the same measurement between 6 and 7, but it's being done on 3 different scales, A, B, and C, which could represent 3 different kinds of metric rulers. The same value on different scales may need to be recorded differently because we want to be intellectually honest about how precise our measurements actually are. So this is one of the reasons why good scientists often adopt significant figures when they're actually recording measurements. We'll talk more about that shortly. Each of these rulers are being used to measure the same length in the same place, but they will not give the same recorded value. So A, it's going to be, that arrow is somewhere between 6.6 and 6.7. Whereas B, it's somewhere between 6.5 and just 7. And C, all we can say is it's somewhere between 6 and 7, maybe a little closer to 7. Different instruments give us different amounts of precision, and so the numbers we use have to be reported differently. Illustrates that this is a subtle problem. So when you use this illustration, you're asked to answer questions about different distances based upon the lines, the numbered lines that appear above the meter stick. So read those questions carefully and then spend some time actually counting the lines and figuring out what you can measure and what you actually cannot measure. When we're measuring volumes, we can measure either as cubic centimeters, which is for a solid, or for liters as a liquid. Now, the cubic centimeter is a derived unit. It's calculated by taking 3 dimensions of length. How long, how wide, how high. It's the base times the length times the height. So if you have a cube where each side is 1 centimeter, a tiny cube like a sugar cube, it's 1 times 1 times 1, but we say 1 cubic centimeter. Now in your study guide, we pose the question, well, what if your cube had each side, each dimension was 4? Well, instead of 1 by 1 by 1, it would be some other number. It would be 4 cubed, but you would still give the answer, whatever the number is, in cubic centimeters. Which is a derived unit. The liter is a base unit of the metric system, which happens to equal 1,000 cubic centimeters. So now with our cube, instead of imagining it with each side being 1 or each side being 4, let's again imagine that each side is 10. If each side is 10, then it's going to be 10 times 10 times 10, which is, of course, 1,000. And now we can see that this is a cube made of many, many cubes, 1,000 cubes. Each one of those cubes is 1 cubic centimeter, but there are 1,000 of them. And so that 1,000 cubic centimeters, well, it equals 1,000 milliliters, which is the same as 1 liter of water. And, well, 1 liter of water has a mass of 1,000 grams or 1 kilogram. Now, these nice round numbers are not a coincidence. The metric system has been designed so that with liquid water in a certain range of temperatures, we have this nice arrangement where if you know the volume, you know the mass. So that is a very cute thing. It's been rigged this way. And if you know the volume, you can approximate the mass. It's a very clever trick. And so you should memorize that fact because it comes in very handy in science courses. Now, another problem with measurement occurs with using a graduated cylinder, and students often underestimate how to use it, and they don't acquire the skill. They don't rehearse the skill, and it really shouldn't be taken lightly. Because water has a property which is called adhesion. It basically means water has a weak attraction to other molecules, which should include the sides of any container. That is, if we put water in a graduated cylinder, some of those water molecules are going to be try to stick to the inside of the graduated cylinder. Because that is true, the column of fluid, the water in a test tube or graduated cylinder is not going to lay perfectly flat. It's not going to be a straight line. You're going to get a curve, which is called the meniscus. And so, do you read the top of the curve or the bottom of the curve? Well, it turns out the instruments have been rigged in such a way that you're supposed to look at the bottom of the curve. That means you need to get your eye lined up with that bottom of that curve, with the meniscus. And if you don't, you're either going to underestimate or overestimate the amount of fluids that you are trying to measure. And that could be a certain amount of error that leads to a bad result. So it's really important that you get in the habit of always making sure that when you're measuring in a graduated cylinder, that your eyeball lines up with the bottom of the curve, the meniscus. These cautions about the metric ruler or how to read the graduated cylinder, I'm sharing these with you because, frankly, there's no such thing as a perfectly accurate or perfectly precise instrument. There's limitations. Yet at the same time, we want our experimental data to be valid. We want our quantities to be expressed, both in terms of their accuracy and their precision. So one way we try to deal with that is through significant figures. Precision are often used as if they mean the same thing in North America, but that's not the case. Accuracy is how close the number is to the actual or desired value, while precision is whether or not the numbers we have are consistent with each other. Are they easily replicated or easily repeated in future trials? To help you understand that distinction, we're going to use these figures of an archery target. The center of an archery target, of course, is the bullseye. If we get a result that looks like this, well, all the arrows are in the bullseye and they're all tightly packed. So it's very accurate. They're hitting the target, but it's also precise because they're hitting it in almost exactly the same place each time. High accuracy, high precision. But if we get this result, well, the arrows are tightly packed, but they're not centered in the bullseye. Well, this tells us that there's a source of error. We have low accuracy, but high precision. This is what you get when the instrument, the tool you're attempting to measure things with, it's doing a good job, but maybe there's some human error. Alternatively, we can get a result like this, where everything is clearly centered around the right target, but it's low precision. This would be the human beings doing a good job of aiming at the target, but perhaps the equipment is a little unreliable, a little unsteady itself. We can use these last two examples to try to figure out what's going on when we get data that doesn't match what we expect. If we get low accuracy, we know it's probably human error, and there's a way to adjust for that. But if we get low precision, we know it's probably a problem with the equipment, and there's a way to adjust for that. But if we get this result, low accuracy, low precision, well, probably we're going to have to start over because we don't know exactly what went wrong. A whole bunch of things could have gone wrong. And that may sound frustrating, but that's just the nature of science, and that we evaluate our measurements, and if we consistently find flaws in how we're measuring things, we got to stop, take a breather, and figure out how we're going to handle it. Now, one way we can handle it after the fact is to, show some caution in evaluating the math, any calculations that we conduct based upon our measurements. The basic idea is the result of a calculation should not have greater precision than any of the numbers used to calculate it. For example, 4.2 times 1.77 equals 7.434. Well, that's certainly a true statement. But 4.2 has 2 sig figs, while 1.77 has 3. And our answer, 7.434, it's got more sig figs than either one. Well, since the two numbers used to calculate the answer have less precision, there simply is not enough certainty to accept the result of 7.434. We can't claim to have a result that's more accurate than any of the numbers used to calculate it. We can't claim to have an answer that's so much more precise than any of the numbers used to calculate it. To be reported in a scientific paper, that number needs to then be rounded, in this case to just 2 sig figs, so it would be 7.4. And that way we are accurately reflecting the precision in the original measurements. The use of significant figures becomes even more important when we're talking about ridiculously large and ridiculously small numbers. Since particles are so tiny, chemists and other scientists must sometimes use very small numbers. For example, this is the mass of a proton. It's a zero, a decimal point, followed by 30 more zeros before we get to any significant digits. There's only 3 significant digits here, 1, 6, and 7, preceded by 31 zeros. What a pain in the neck that is. Now, the number of these tiny particles in something like a glass of water is huge because they're so tiny. We can fit a lot in there. And so chemists sometimes have to use very large numbers. 50 milliliters of water will have 30 septillion water molecules. That's a 3 followed by 22 zeros. Again, kind of intimidating. So we have one number that's ridiculously small with actually only 3 significant figures, and we have one other that's really, really large, but only only 1 significant figure, the 3, the very first integer. What to do? I mean, this is impractical. We need an easier way to handle these kinds of numbers. Fortunately, there is an easier way to deal with them by expressing them as multiples of exponents, sometimes called powers of 10. So again, we could write this, the mass of a proton, or we could write this. A lot easier. We could write out the number of molecules in 50 milliliters of water, which is tiny. But it's a lot easier to skip all the zeros and write it like this in scientific notation. Another advantage, this notation is the same way we can enter these numbers in a calculator. Most affordable calculators have a button to make it easier to enter numbers in scientific notation. It could be EE or EXP or 10 to the X, but in any case, you need to know how to use what button you have to enter very large or very small numbers. Ideally, the way you write it on your paper is the same as the way it looks when you enter the steps into a calculator. Now, the phenomena that we describe and measure in our observations, they inspire us to propose explanations. The hypothesis, which can be tested via experiment. This involves C, E, R. This is an acronym that stands for claim, evidence, reasoning. A claim is expressed clearly and accurately in a complete sentence. In your writing, students, in your notebooks or in the work you hand in, I often use these little pieces of shorthand to talk about problems with the way you set up a sentence. If it's not a complete sentence, I write CS. If you're not referring to the original question, I write RQ. If you fail to show evidence of reasoning, I go ER. None of these are things that you want in your comp book or any other work you submit in this class. It means that you're failing to clearly communicate your claims. So be aware of that. The claim that we're doing is essentially addressing a question or a problem which is already under investigation. It must be supported in turn by evidence. Evidence should include quantitative data, that's the numbers, and also qualitative data. These are words where we write out what we observe, what we detect with our senses. Evidence should be based on more than one trial. Here we have each dot representing a particular result that you get in a particular trial. No group got 18 or 22. There's just one group that got 21 and 24, but there were 4 groups that got 23. In general, good data is lots of data, and poor data is no data or very limited data. Whenever possible, your evidence should include references to other texts. Scientific papers, when they get written, they typically refer to other people's work. They build on other people's evidence. So their evidence becomes part of your evidence when you write a scientific paper. It makes your claims more powerful. Your evidence, though, has to be testable. You can't just say, hey, I did this experiment, I got this result, I'm a genius. That's not the way it works. Instead, you say, hey, I investigated this thing, I did an experiment, and we did all these particular steps with just this amount of material and just this order, and we analyzed it this way, and we got this result. You got to describe it so well that anyone else can read your paper and do the same experiments you did. Otherwise, if you can't make that kind of description, if you can't do that, then your paper is not likely to get published. We have standards, and so you have to show that you have evidence which is testable, and it has to pass the test. Now, reasoning is interesting because it's usually a piece of logic that connects your evidence with your claim. So reasoning connects the evidence and explains why the evidence proves the claim. And so it kind of works backwards from the way we present how CER works. That is, the reasoning connects our evidence with the claim. We say CER because that's the order we do it, but at the end, what we say, we explain how the evidence proves the claim. Now, I'd like to give you an example of a claim from the ancient world. Philosophers of the ancient world, thinking about the way different kinds of matter behave, they were led to consider the possibility that all matter was made of invisible particles. One philosopher, Greek, was Democritus. He lived around 460 to 360 before the Common Era, before Christ. He claimed that there must be particles smaller than the human eye can see. And these were the smallest things possible. And he called them atomos, which in Greek means uncuttable or indivisible. And this relates to the video we showed in class, The Lives of Stars, where Carl Sagan begins by saying something very strange. He says you wish to invent the universe, you must first bake an apple pie from scratch. And he goes on to talk about cutting the apple pie in half over and over again. Well, it seems silly, but he's actually saying something very wise, because he's referencing the fact that you can keep cutting and you eventually come to particles so small that we used to think that they were the smallest things that could be, that they were effectively uncuttable. Now, Lucretius developed this idea of Democritus, and he presented many indirect arguments for these atoms. And he did it in a poem called De Rerum Natura, which is Latin for On the Nature of Things. Now, Lucretius's book was in Latin, and Latin is a dead language. It's not spoken by any living communities, but it is a language of scholarship, and we often use Latin words and terminology, prefixes in science, including in biology. Names for organisms of species, the names we give are Latin-based names. But the reason people still study Latin today is because it allows us to study events and histories set by the ancient world. So don't worry, you don't have to learn Latin in this course, but let's make sure that we understand the logic that Lucretius is able to present, which he originally did by writing in Latin. Lucretius says, "We see the cobblestones of the highway worn by the feet of many wayfarers. The bronze statues by the city gates show their right hands worn thin by the touch of travelers who have greeted them in passing," right? The cobblestones wear smooth. The hands of the brass statue, the bronze statue, they would get worn smooth. In fact, Lucretius goes on to say that pretty much everything is being diminished in this way. Everything is being worn away. But then Lucretius adds, but to perceive what particles drop off at any particular time is a power grudged to us by our ungenerous sense of sight. What Lucretius is saying basically is the particles must be dropping off, but we don't see them because they're too small. They're too small to see. So this is actually pretty keen reasoning, but neither Democritus nor Lucretius ever bothered to do anything other than report the claim and say how they reasoned it. They didn't actually do experiments to test their ideas. And it's actually not that hard to do an experiment to test the idea. It's kind of a shame that they didn't get around to it themselves. It could be as simple as more flavor or less. This is the previous lab, the chewing gum lab. In this lab, the gum's mass clearly decreased, but at no time did we see any part of it leave. So the gum must be made of a large number of particles too small to see. In other words, we tested the idea that atoms are real. We are basically using the idea of atoms to explain why the gum loses its flavor over time. So now let's see if we can use it to explain not just the flavor of gum, but how different flavors of matter are made from even smaller particles combined in different ways. So atoms do appear as elements in the periodic table. Here the pink spheres represent protons and the gray spheres neutrons, and the pulsing green area, the location of where the electrons are moving. All the elements in the periodic table are believed to be made of the same set of particles, and yet they're all so different. We have silver, which is a solid. We have helium, which is a gas. We have mercury, which is a liquid. And yet they're somehow made of all these particles, including the pink protons and gray neutrons, which are shown here, greatly exaggerated in the nucleus of the atom. The protons and neutrons contain almost all of the mass, and the nucleus is actually 10 to 100,000 times smaller than the way it's depicted here. So that's where pretty much all the masses of the atom is concentrated. It's concentrated in a very tiny spot. We say it's very dense. And that means all the blue shaded area on the outside where the electrons are moving, well, that's pretty empty and open. It's pretty much empty space. Now, of course, it's not completely empty, but what we mean is there's almost no solid matter moving outside the nucleus. What's moving instead are the electrons, which have almost no mass, and they move so rapidly that they are basically creating a field of force. And that's why atoms, when you push them against each other, they don't typically break, they resist it, they behave as if they were solid, because the empty spaces that surround the nucleus are a field of force. Now, to talk about this in any detail, we have to talk about particles, which are actually smaller than the atoms themselves. Here we have a picture of a crystal of diamond, which is a very valuable version of carbon. It's actually pure carbon. And, well, like everything else made of carbon, it's made of carbon atoms, and the atom has a nucleus. The nucleus, you can see, has the protons and the neutrons. And we can talk about the properties of the proton and the properties of the neutron. And outside the pink and gray spheres, we have this region that's kind of glowing green. And this is the electron cloud. It's hazy. We don't know precisely where the electrons are, but we could talk about the properties of the electrons as well. So we have these three subatomic particles that we're going to use to attempt to build our model of the different kinds of atoms. subatomic particles, a proton, neutron, and electron, and we want to summarize all that information efficiently. So in our study guide, we've made a table, and we're going to compare them in terms of their symbols, in terms of their mass, in terms of their charge, and in terms of their location. Protons glow pink if you excite them. We use the symbol P+. And we say by convention that they have a mass of 1, an atomic mass unit of 1. Protons are positively charged, and they are found in the nucleus. Also found in the nucleus is another particle that by convention we often treat it as if it also has a mass of 1. But this particle, the neutron, as its name suggests, is neutral. Now, I want to make things easy for my students, but I also want to be honest with you. The protons and neutrons are not precisely equal. There's a slight difference in mass between the two. But in our course in biology, it won't matter. But later on, you'll learn that the masses are slightly different, and the difference in mass can be useful in explaining things like nuclear reaction. But today, we're just going to treat them like they're both the same in terms of their mass. One's positive, one's neutral, and they're both found in the nucleus. In the same way, the electron, it glows green when you excite it. We use the symbol all scientists do, E-, and we treat it as if it has 0 mass. Where do we find it? Well, somewhere out there in the cloud, moving outside the nucleus and carrying with it negative charge. Now, again, to be completely honest with you, in this course, it doesn't make sense to talk about the mass of an electron, but there are places in science where we do have to discuss the mass. It's actually not 0, but it's so small we can treat it as 0 in a course like this. 1,867 times smaller than the proton or the neutron. Now, again, even though all the atoms are made of the same 3 subatomic particles, they're all made of protons, neutrons, and electrons, well, they're all pretty different from one another. For example, silver is a shiny metal. It's a solid. Mercury is a liquid. Helium is a gas. And the various elements differ from one another in a whole bunch of different ways. So somehow, we have to use these 3 particles, which are all the same, to explain the elements, which are all very different from one another. Well, let's remember that matter is made of atoms, and the atoms are made of these subatomic particles that we find either in the nucleus, the electron cloud, but they all end up arranged as elements within the periodic table. And we define an element as the simplest form of matter which has a unique set of properties. So, that's just kind of how it works. We start off with this, the basics are the same for everything, and then somehow by putting them together in different ways, we end up with a bunch of different elements. Well, it may be helpful to remember that the elements are just listed in order of their atomic number, which is equal to the number of protons in the nucleus. Basically, they're listed in order of their complexity. Now, in a neutral atom, the number of positively charged protons in the nucleus must equal the number of negatively charged electrons in the outer shells. So not all atoms are neutral, but if we just begin with that, we can say, oh, if we know the number of protons, we also might know the number of electrons, and that could simplify things. Here's something else that actually simplifies things. Protons and electrons are both elementary particles. So since that's true, they always come in whole numbers. There's no such thing as 1/2 of a proton or 1.5 electrons. They're just counting numbers. It's just arithmetic. And so that can make things easier too. So with that in mind, here's a picture of the nucleus of an atom of carbon. Again, we see 6 protons in pink and 6 neutrons in gray, but now we have this vague blue-green region. We don't see the individual electrons. What is happening? Well, what's happening is that the protons and neutrons are somewhat localized. We kind of know where they are. They're found in the nucleus, where almost all the mass of the atom is found. But the electrons, at the same time, they are in motion outside the nucleus. So we don't see the individual electrons, in part because they're moving very rapidly. And another reason we don't see them is because they're moving. They're not moving in a regular, predictable motion, which is surprising. Electrons do this strange thing because they aren't really going around the nucleus the way a planet goes around a star. People often look at a picture of the atom, they think it reminds them of a solar system, which of course we studied. But they're not really like that. Instead of having a regular orbit, we say that the electrons occupy or fill up levels of energy. And we sometimes call these energy levels shells, and sometimes confusingly, we call them orbitals. But please remember, it's not like a regular orbit. Instead, they fill up the energy level. And the electrons with the greatest energy are those whose shells are the farthest from the nucleus, because the shell being farther away, it's bigger, so it takes more energy to fill it. Here we have an illustration that reminds us of some basic facts. First is the first shell, the one that's closest, it's not very big. It can hold a maximum of 2 electrons. The second and third shell can both hold 8. And if we were to do chemistry, we'd learn about the number of electrons in a whole bunch of other shells. But to keep things simple, first shell 2, second and third shell 8. Now notice we have pictures here that compare carbon and nitrogen and oxygen, and they all have 2 shells. But just because they can hold 8 electrons in that second shell doesn't mean they will. In fact, there are empty spaces. Carbon has 4 filled spaces but 4 empty spaces on its outer shell. Nitrogen has 5 filled, 3 empty. Oxygen has 6 filled and 2 empty. But there's a total of 8 spaces there. And each one of those is a different pattern of filled and unfilled spaces. And it's this arrangement of how the electrons actually are in the outer shells that determine why different elements act differently when they're doing chemical reactions. Now, again, we have this misleading term. Again, in the pictures here, the paths of the electrons look like they're moving in circles, like they're in orbit. So let's talk about that in a little bit more detail. Orbitals aren't regular paths, but they are the place where an electron is most likely to be found. Remember the description we had in the pictures that we talk about an electron cloud, where you don't actually see where the electron is precisely at any given moment. It kind of looks like it's everywhere at once inside that shell. But all we're saying is it's just the place where they're most likely to be found. Now, the orbitals that are on the outside, we say S and P orbitals, the ones that are on the outside, they determine the atom's properties. And again, that's because of the number of filled and unfilled spaces affects the way the atom behaves. Less obviously, the way the electrons share this space, the outer space, the way they share the orbitals plays an important role. So for example, here we're not saying that this dumbbell shape is the actual shape of the orbital. What we're really saying is this is a way of describing where it's most likely to be compared to the rest of the space. So the area that's shaded is where the electron is most likely to be, and the area at a right angle to it, it's less likely to be. It's very unlikely to be there. Different orbitals have different shapes. These are s orbitals. This is like the very simple basic orbital that surrounds the simplest atom, hydrogen. It's just basically a round ball. As we go up to the next energy level, we start having more possibilities. We have 3 possibilities on different axes, X, Y, and Z. At the next energy level, we have paired axes. And so instead of a dumbbell shape, we've got double dumbbells based upon two groups of axes. At a higher level, we start getting even weirder and more exotic shapes. Notice that the yellow and green shapes don't actually touch. And this is very strange because electrons actually, if you give them energy, they can hop from one shell to another. They can hop up to a higher energy level. In this case, you ought to be able to imagine that they hop from one place to another, but they're not traveling in the space in between. They're just going to another energy level. Now here we have an animation, and it shows the simplest kind of orbital. It's a sphere. And now we imagine three p orbitals on three different axes. And if you look carefully, you can see that none of them are sharing spaces. That is, none of them are touching either. Then at the next energy level, we start seeing paired axes. Instead of just one axis, there's two. Like that's YX, and then the next one will be XY, and so on and so forth. Eventually, to keep sharing the same space, even though it's a larger orbital, the shapes get weirder and weirder. I especially love the last one in bright purple, which kind of looks like a donut. We call that a torus. Now, if we could keep going with this animation, check it out. The different shapes are what allows them to share the space. There's your s orbital, and then we see how the three p orbitals fit around the s orbital, and then we start fitting in the d orbitals with the different shapes. Eventually, at the end, we actually have that little purple piece, little donut, and it all fits. Now, believe it or not, all those crazy shapes and all that crazy mathematics is inside the periodic table. The periodic table was first proposed by Dmitry Mendeleev in 1871. He didn't know a thing about electrons, protons, or neutrons. He didn't know a thing about orbitals. None of that stuff had been discovered then. What he was looking for was a way of classifying the elements he knew based upon their different properties. You know, some elements were, you put them in water, they'd react violently, they'd explode. Other elements wouldn't do anything, they were super stable. You know, different things would happen to different elements. So he would arrange them in a pattern, and he found a pattern and he made a prediction. And his particular prediction turned out to be testable. He actually predicted elements that would be discovered that were unknown, but they would fit in certain places on his table. The table is organized in two ways. You can go up and down columns. These are groups or families. We call them groups or families because elements in the same group tend to act the same way chemically. We can also talk about going right to left and vice versa along a row. The name of the rows are periods. That's why it's called the periodic table. And the meaning of the period is one electron is added every time you move to the right in one of these periods. Now, to use a periodic table, we just have to know a few things. So the symbol in the middle is X. That gives the name of the element. If you need just one letter, that letter is capitalized. If you need a second letter, it's lowercase. So capital C is carbon, but capital C little a is calcium, capital C little d is cadmium, capital C little u is copper, and so on and so forth. Above the atomic number, we're going to have, above the symbol of the element, we're going to have the atomic number, which we sometimes call the Z number. The Z number, the atomic number, it identifies the element. It's equal to the number of protons. And again, the protons come in a whole number. If you've got one proton, if your Z number is 1, you're hydrogen. If you've got 2 protons, your Z number is 2, your helium, and so on and so forth. Now, if you're a neutral atom, if your atom doesn't have an overall charge, then the number of protons, positive, has to equal the number of electrons, negative. Now, they don't always do that, but when we first start drawing atoms, we'll often assume that they're all neutral because it makes it easier. We just pretend that the number of all the particles inside the atom are the same, and that makes it easier to figure out how to draw the structure. Now, in addition to the atomic number, which is a whole number, a Z number, which appears at the top, we have the atomic mass. I'm representing it with a number sign, not a number and not a letter. That's because the atomic mass is not about the individual atom at all. It's about a sample of that element, a sample that contains many, many, perhaps millions of the same element. And those atoms, even though they might all be the same element, they're not going to be absolutely identical. And so we're taking an average of the mass, which may not be the same. We say it is the weighted average of the masses of that element's isotopes. Because it's an estimate, it's never going to be a whole number. We're not talking about an individual atom, we're talking about an average. That average is usually expressed as a decimal rather than a whole number. And that average is the average of the mass, not just of the protons, but of all the protons and all the neutrons in a given sample. An example of an isotopes that we love to use in biology is carbon 12. Isotopes are atoms of the same element, but they have different masses. They differ in the number of neutrons. You can add a neutron and add more mass, but it doesn't affect how it behaves chemically because neutrons don't have a charge. They don't affect the charge of the protons. They don't affect the arrangement of the electrons. They don't affect any of that stuff. All they do is add mass. So if we have a neutral atom and everything's the same, then we would have 6 protons and 6 neutrons, and 6 plus 6 is 12. So we have a version of carbon that's called carbon 12. 6 protons, 6 neutrons. That's the most common form of carbon. And if you look at the number in a periodic table, that estimate that appears under the symbol for carbon is just a little bit more than 12. It's like 12.01. If every if every carbon atom in the universe was carbon 12, then there wouldn't be a decimal underneath the symbol for carbon. It would just be 12. But you see, there is a carbon 13 that has 6 protons and 7 neutrons. And there's a carbon 14 with 6 protons and 8 neutrons. And there's other isotopes, less and less common, but they still exist. So why is the decimal underneath carbon not 12? Why is it 12.01? Why is there a little bit extra? Because a tiny percentage of carbon atoms have a few extra neutrons. We call those isotopes. Now, when we're drawing atoms, sometimes we're going to have to deal with these extras. We may eventually draw atoms that have extra neutrons, or we might draw atoms where the number of protons and electrons aren't the same. These things exist and they are important. But for right now, let's just remember the atomic number gives us the number of protons. It's a whole number. If it's a neutral atom, it's the same number for the electrons because the charges have to balance. And the estimate under the bottom, well, that's not for an individual atom. That's for a sample of atoms, and it just is an estimate of the average mass of all the protons and neutrons that that atom possesses. Now we're going to deal with an individual atom. We use the average atomic mass to express the masses of all the isotopes in that sample, but we're going to deal with an individual atom. we use nuclear notation. And here we use the A number and the Z number. Again, the Z number is just the same as the number of protons, and the A number is an attempt to record the mass of all the protons and all the neutrons. So it's basically just the number of all the protons and all the neutrons. We'll put the mass number, the A number, on top. We'll put the atomic number, the Z number, on the bottom. And if we were going to do that for the most common version of helium, we'd have helium-4 with 2 protons and 2 neutrons. Since the atomic number is 2, we put that on the bottom. That's just the number of protons. Since the mass number is 4, there's 2 protons plus 2 neutrons, we put 4 on top. And that's how we write it. Notice, by the way, that if we take the mass number and we subtract the atomic number, the only thing that would be left would be the neutrons, because we'd be subtracting the proton part. So the difference between the mass number and the atomic number, A minus Z, equals the number of neutrons, which is N. Or, as I like to say, A minus Z equals N. To help you remember this, just remember, you're amazing. A minus Z equals N.